Okay, now I'm seeing people. Okay. So can they hear me now? Yeah, okay. All right, so y'all who are on Zoom, I talked about some things at the very beginning, so stick around at the end of class and I'll go over them again. But we're doing iClicker right now. So just jump in on that. So I'll give y'all another 20 seconds. Okay, so everybody clicked in. Turn and talk to the people around you and click in again. Looks like people were pretty sure on their answers on this one. So I'll give y'all, what do you say, to 45 seconds. All right, so what did y'all say? Not that one. This one, very good, C, and then 100%, very nice. Okay, so we know that NH3 is a base because it accepts protons from water. So what does that look like in a reaction? Right, and we said it's weak, so do I have a single arrow or a double-headed arrow? A double-headed arrow. It looks like that, so we can go forward and reverse. What happens? If NH3 is a base, it's going to do what? Accept a proton. So if it accepts a proton, how do I write it? Add a proton. What's a proton? A hydrogen ion. So instead of being NH3, it should be NH4, but it's charged, so it's going to be a +1. Then what's left? OH minus. This is what makes NH3 a base, because when we put it in water, we make OH minus. That's what makes it a base, right? It's not a traditional sense in the base, right? If you had NaOH, if you put it in water, what do you make? Na plus OH minus. You can see the OH. You can see it's going to be disassociated, but here you can't see that until you really think about it. But they're both bases. Okay, we got one more. All right, so thinking about that same definition, right? So according to that Bronsted-Lowry definition of acids and bases, when an acid is dissolved in water, so if you take that acid and you put it in water, it does what? Please cover your noses with your masks. I'm supposed to call it at 1 minute, so click in, give you 10 seconds. Okay, turn and talk to the people around you. Okay, so 45 seconds. Don't forget to click in again. Okay. So what did y'all say? All right. So, oh, but we changed quite a few people's minds. Okay. So when you were looking at this, right, we know if it's an acid, it must donate a proton, right? It must. So it can't accept a proton. That's a what? That's a base. And when an acid is dissolved in water, it neutralizes the water. No, an acid neutralizes a base neutralizes an acid. So you can't, that's not true. So donates a proton. Y'all are 100% right about that. Now, what happens when it donates a proton? Remember when we did these double-sided arrows, right? And you started out with something that was a base plus water. What happens? Oh, we're starting with an acid, not a base. What happens to that acid when you add water? It loses that proton, right? And then it becomes something different. It becomes a conjugate base. Because if we go in the opposite direction, the base can turn back into the acid. And all you're doing is switching back and forth, right? Okay, so we're going to apply that later today. So let's switch gears and let's go to our in-class problems. I think we just didn't quite finish the last one in section 2, right? Okay, so we have a neutralization reaction between H2SO4 aqueous plus NaOH, and it's a solid. So what's going to happen in this reaction? It's neutralization. What are we going to make? Yell it out. What are we going to make? Water, and we're going to make a salt. And sometimes what? CO2, but only if you have carbon in one of the reactants. Do we have carbon in one of the reactants for either A or B? No. So no, all we're going to make is a salt and water. Those are the only two things that you can make. So what I like to do is I like to make the water first. So I know from one substance, I'm going to get a hydroxide. And from another substance, I'm going to get what? A hydrogen. So I'm going to come over here and make HOH or H2O. Same thing. What do I have left? I have Na and I have SO4. That gives me a metal and a polyatomic ion, right? That's a salt. A salt can be, what can a salt be? A metal and a non-metal. What else can it be? A metal and a polyatomic and a polyatomic, right? You remember this from way back when. We're talking about ionic compounds. That's what a salt is, an ionic compound. So what I'm left with, start with the metal. What's the metal? Is it Na or SO4? Na. And then I have my SO4, but is that the right formula? Well, so if I go to my periodic table, what's the charge on Na? +1. Now go to your polyatomic ion table on your best friend and go find SO4. What's the charge on SO4? Now please keep those masks over your mouths and noses for the entire class. So what's the charge on SO4? 2-. So all I have to do is cross them to get my formula. If I have a 1, I don't write my 1. I just write the 2. So I would write Na2SO4. So I'm going to go ahead and put that 2 in, Na2SO4. Am I balanced? I'm not balanced. I'm not balanced. You could do one of two things. You could look at the waters, or you could look at the salt to balance the salt. What do you want to balance? So look at sodium. How many sodiums do I have on this side? 2. How many sodiums do I have here? 1. So what do I need to do? Put a 2. So I have 2 NaOH, which means that I had 2 OHs, and I used 2 hydrogens over here to make water, right? So I did this twice. I did OH, and then I pulled an H, and I pulled an H. So how many waters did I actually make? Am I balanced? Yeah, I'm balanced. I'm balanced. So you don't necessarily have to think in terms of atoms. If you kind of think in terms of units, you know, like this OH works together, right? Okay, can I erase this? So I have room for that next one. Okay. Oh, and the N2SO4, I just saw this. What do I need to put? States of matter, it's aqueous. And water was what? Water was what? A liquid. Okay, good. Make sure to put our states of matter for next time. Okay, HBr, aqueous, plus LiOH, solid, yields. What are we going to make? A salt and water. So let's put our water first. Water is H2O. So I'm going to get a hydroxide from here and a hydrogen from here. And I make liquid water. What is left? Lithium, which is a metal, and bromine, which is a non-metal, and it's going to be aqueous. So is this the right formula for lithium bromide? Yeah, lithium is a +1, bromine is a -1, so 1 and 1, you just don't write them. Am I balanced? Yeah, so I'm good. We did great. Okay, so the next thing we're going to talk about is chemical equilibrium. Now, chemical equilibrium is really important because when we talk about chemical reactions happening, remember how we said some of them go to completion? This means it's 100%, right? So if you had NaOH and you put it in water, all of it would disassociate into what? Na plus OH minus, right? That's 100%. That's why we write that one forward arrow. But what happens when you see something like this? That forward and reverse arrow. What does that tell you? It doesn't fully disassociate. So basically, when we have a full arrow, that's telling me that I have 0% that is NaOH, and I have 100% that has disassociated into sodium ions and hydroxide ions, right? But if I have this double-sided arrow, well, maybe I have 50% as the reactant, and here's my product, and maybe I have 50% that's the product. That's a possibility, right? But what else is a possibility? Everything else. 1% and 99%, right? And that percent or that ratio determines how strong an acid or a base is, right? So something that disassociates 99% is very close to a strong acid or base. But what if something that's the reverse? What if it's 99% reactant and only 1% product? This is very what? Very weak, because you aren't making very much product, right? So for every single individual chemical reaction, those are unique percentages. And it depends on the substances that are in that reaction. They're all unique. And so the way that we describe that is that we say that each reversible reaction has an equilibrium. And when that reaction reaches equilibrium, it's done adjusting and it stays wherever it is, whatever those percentages are, it stays. But does that mean, look at the reaction that we drew right here. Does that mean that we have an equal amount of reactant as we do product? Do I have the same amount of reactant as I do product? No, I have way more reactant. What it is telling me at equilibrium is that if any reactant turns into product, that same amount of product is going to turn back into reactant. So the rate going forward is the same as the rate going backwards. So it's an equal rate. Let me give you a different example. Now, bear with me. I'm going to give you a sports analogy. I'm sorry. Football, right? How many people are on a football team? The whole team. A lot. 50, right? Of those 50, how many can be playing at any given time? So how many can be on the field? Only 11. So how many are on the bench? 39, right? So this is just like a reaction, right? I have the bench here and I have the field here, right? So if I have my 11 players on the field, if somebody comes off the field and goes to the bench, what has to happen or I'm disqualified? I got to send somebody from the bench to the field, right? So the rate of somebody going off the field is equal to the rate of somebody going onto the field. But that's football. That's one reaction. How about basketball? Is it the same, 11 and 39? No, in basketball, how many people can be on the court? 5, it's only 5, right? So my ratios of players being on the field or on the court is different than those being on the bench, depending on what game I am playing. So the same is true. It depends on what chemical reaction I'm talking about. But the concept is the same, that whatever the rate is of people leaving has to be the same as the rate of people going onto the court or the field. So the rate, so when does a reversible reaction reach equilibrium? When the rate of the forward reaction and my abbreviation for reaction is RXN. So when the rate of the forward reaction equals the rate of the reverse reaction. So the forward reaction is going in this direction. The reverse direction is going the opposite. Right? So it's the players leaving the field, the players going on to the field. Same thing. Do you have equal numbers of players in reactants as you do products? Not necessarily. Sometimes you do, but that doesn't mean it's at equilibrium. Equilibrium is an equilibrium of rates. I promise you that there will be a question on the exam, and I'll phrase it. One of the answer choices will be when a reaction is at equilibrium, that means A, B, C, D, right? One of the answer choices will be you have equal amounts of reactants and products. Is that right or wrong? It's wrong. But I'll tell you, lots of people will pick it. So make sure you get this concept, right? Don't get that wrong. All right, so how can we represent these reactants and products leaving the field and getting on the bench and all that kind of stuff? We do what's called an equilibrium expression. So we say K is our equilibrium constant. And that equilibrium constant is unique for every single reaction. That's why it's a constant. It's different for every reaction. But if I can write a chemical reaction for it, that K is going to be exactly the same, whether I have a tiny amount of it or if I have a reaction the size of the university going. Doesn't matter. K is always going to be the same. Because what it really is a ratio of reactants to products. So K, just like we said, is a ratio, but it's the products on top and the reactants on the bottom. Now, why did I put brackets around the P and the R? What do brackets mean? Concentration. So it's the concentration of the products divided by the concentration of the reactants. So remember, it's kind of like the end on top. So when we do this, we have to take into account everything that's a product and everything that's a reactant. And we also have to look at, remember when we were balancing those chemical equations and we had coefficients? That's telling us that we have more of one thing than another. And so we have to factor that into this equilibrium expression or none of our numbers are going to be right. So when we do this, take everything that's a product. So for example, what's a product in A? NBr3 is our product. And we put it in brackets because we're saying it's the concentration of this substance. Now, we have to say that there's more of it. But the way that this works is that coefficient becomes an exponent. So now we have NBr3 squared. So if you were doing the math for this, you would square that concentration value, but you're actually not going to have to do the calculations on it, which is kind of nice. You just have to be able to write the expression. Okay, so now look at my reactants. What's my first reactant? N2. So we're going to put that in brackets and it has no coefficient, so we don't have to worry about that. Now, if you have more than one reactant or more than one product, you multiply them together. So it's not a plus, it's actually, we don't write anything and that shows that we're multiplying. So our second reactant is Br2. But what does Br2 have? Coefficient of 3, so we put it as cubed. Okay. Not too bad, right? Now, B gets a little bit tricky. So if you look at B, what do you notice about this first substance here? It's a solid. Equilibrium expressions are all about concentrations, right? How many players are on the field is really a concentration. So if you have something that's a solid, does it have a concentration? It doesn't. So things that are solids, S, or things that are pure liquids don't have a concentration either. Concentration is always something dissolved in something else. So, or liquids are not included because they have no concentration. Okay, so let's do our equilibrium expression for B. This is B. So we put the letter K, that's our equilibrium expression constant. So our products, here are our products. So we put concentration of CO2 over our reactants. But what did we just say? You just cross it out. Like that's one thing that I do. When I look at those and I see solid, I see liquid, just cross that bad boy out. Get rid of it. So over concentration O2. Okay, good. Questions? All right, so now what does that K mean? You know, like now we can write an expression for it, but so what? That expression will tell us if we write a reaction out, right? If we have our reactants and our reactants go to products, right? If we know the value of K, we can predict what you are going to have more of. Are you going to have more of reactants or are you going to have more of products? And this is really important in terms of predicting what a chemical reaction is going to do. That's really valuable information. So let's do an example. Let's just say I have 10 reactants and I have 5 products. Can you calculate the value of K for me? Well, K is equal to what? Products over reactants. So my products is what? 5. My reactants is 10. Put that in your calculator. What do you get? 0.5. Okay, now what if we swap it? What if we now say I have 5 reactants and 10 products? Okay, it's the same formula, products over reactants. So my products is now 10, my reactants is now 5. What's K? 2. If your numerator is bigger than your denominator, you will always have a value that is greater than 1. So that's this. So if numerator is greater than denominator, K is greater than 1. Does that help us predict things? Absolutely. Because my numerator is always going to be what? Products. My denominator is always going to be what? Reactants. So I'm saying if I have more products than reactants, K is going to be greater than 1. Isn't that awesome? I'm like, no, I think it is. It's really cool because we can make predictions about reactions. We can make things happen. So look at the top one. The top one's the opposite, right? If our reactants is greater than our products, then what? Then K is less than 1. And all you have to know is this formula right here. And then think about dividing one thing by another. And you have your answer. So look at A. 1K, this is telling me that K is equal to 1 times 10 to the 7. Is that greater than 1 or less than 1? Like if I put that in non-scientific notation, that's a 1 and then 7 zeros, 3, 4, 5, 6, 7 zeros. Greater than 1 or less than 1? So K, in this case, K is greater than 1. If K is greater than 1, we have more what? We have more products. It means we're going in the forward direction. You have lots and lots and lots. Oh, down here. You have lots and lots of product, right? You have more product. So in this case, to get K equal to 10,000, oh my gosh, this has to be huge. And this has to be tiny, right? That's what it's telling you about the reaction, how much product and how much reactant you have. It's really awesome. Okay, B, 0.0045. Less than 1 or greater than 1? K is less than 1. So what do you have more of? You have more reactants. Now, I want you to pretend like you don't see C. And I want you to write C in scientific notation. What would C be in scientific notation? -7. Okay, so sometimes I'll give it to you in expanded form, sometimes I'll give it to you in scientific notation. So is 7.9 times 10 to the -7 greater than 1 or less than 1? Very much less than 1, right? So you have to know that that negative exponent means that that number is tiny. But you can always, if I give it to you in scientific, you can always write it out. You know, you have paper, you can do that. So if K is less than 1, what do we have more of? Reactants. Practice that. Will be good. Okay. So why is this important? Well, if we understand the equilibrium of any given equation, we can change parameters of that equation, of that reaction, and make it do what we want. So I can take, for example, this reaction here. So I have lead 2 iodide. This is lead 2 iodide that is produced when we cool lead 2 and iodide ions from solution. So here are my reactants, and then here are my products. If I'm producing heat, what kind of a reaction am I? I'm exothermic. This is a great example of an exothermic, E-R-M-I, exothermic reaction, right? It's giving off heat. That's exothermic. Okay, so what's really cool about chemistry is that if I change one of the reactants, or one of the products, then the chemical reaction will shift in order to basically negate what I have done. Because you're going to stress the system, and the system is going to have a response to it. So if I want to drive this reaction in the forward direction, I can do that. If I want to drive it in the reverse direction, I can do that. And it's all about changing either one of the reactants or one of the products. So when you look at a problem like this, and it says, what direction will this reaction go? Will it shift left or shift right? If I'm going to have a shift in this direction, what is that? Is it a right shift or a left shift? I'm going in what direction? I'm going to the right. Okay, so if I go in this direction, what am I doing? This is a left shift. Okay, so the question is, how do I make the equation go to the right or make the equation go to the left? So I'm going to look at these different things that I can do. So let me kind of make a little table. Okay. So let me put this up here. I need that room. So if I go this way, it's left. Okay. So we are going to stress the system. We are going to do something. And then the reaction is going to have a response to that. So this is what the reaction will do. And then that's going to tell us what the shift will be. Is the shift going to be left or right? If you do this, you're going to be able to answer every single problem like this. So add iodide. This is the ion. Is that a reactant or is that a product? I minus, reactant or product? That is a reactant. So if we add it, are we going to increase or decrease the amount of reactant in the reaction? We add it, that will be an increase. So the reaction is going to do the complete opposite in response to that stress. So wherever your arrow was up, make it go down. Right? So if we increase reactants, the reaction will decrease reactant. How do we decrease the amount of reactant in this reaction? Do we shift left or do we shift right? If we shift right, we make what? Products, right? If we shift right, we make products, and we basically lose reactants at the same time. So make product and lose reactant. A left shift is the opposite. A left shift, we're making what? Reactants, and we're losing products, right? So if we increase the amount of iodide ion, the reaction will decrease it. And how are we going to shift, left or right? We want to decrease the amount of reactant, so we're going to make more product. Make more product is a right shift. I know, I think I'm gesturing the opposite way for y'all. I need to not do that. All right, look at B, heat the reaction. Where do you see temperature in this equation? In the reactant side or the product side? In the products. So am I increasing the heat or am I decreasing the heat? I'm increasing the heat. So the reaction is going to do the opposite. It is going to decrease product. How do you decrease product? You shift left. Okay. Remove lead-2 iodide. Lead-2 iodide is a product or a reactant. It's a lead-2 iodide is a product. So if we remove it, it is decreasing. The reaction will have the opposite response, and it will increase product for a right shift. Okay. Cool the reaction. Where do you see temperature in this reaction? In the products. Temperature, whether you're heating or cooling, doesn't matter. Temperature in this reaction is in the product. If you cool the reaction, are you increasing or decreasing the amount of heat? We decrease it, so the reaction will have the opposite. It will increase. So how do we increase product? Right shift. So just by heating or cooling a reaction, I can drive it in one way or the other. Isn't that cool? It's awesome. And chemists use that all the time. Okay, so I want you to try 9.27. I was supposed to do this one in the video, but I didn't apparently. You try this one. I'm going to set up my chart. You do the same thing. And then we'll come back and check answers together. So once you have your answers, talk to the people around you and see if you all get to the same answer. And on Zoom, if y'all want to talk to each other, y'all are welcome to do that once you get some answers. Don't forget, when you get an answer, share it with the people around you, see if they came up with the same thing. Okay, so let's look at A. We add O3. O3 is ozone. So this happens in the atmosphere where you have just atmospheric oxygen, O2, that gets struck by lightning, which provides a heat source, which converts to ozone, right? And ozone protects us from UV radiation. Y'all know about the ozone hole and all that? Yeah, okay. So add O3. O3 is ozone, right? So that's a product or a reactant. That's a product. So we increased a product. What will the reaction do? Decrease the product. What is our shift? Left. Right? We're decreasing product. It's going to be a left shift. Okay. Add O2. O2 is a reactant. We're going to increase it. Reaction will do the opposite, which will decrease it. If we want to decrease reactants, we're going to shift right. Okay. Raise the temperature. Temperature in this case, now what kind of a reaction do we have? This is an endothermic. You have to put energy in to make this reaction go. So to raise the temperature, are we going to affect a reactant or a product? A reactant, and that reactant will go up. So the reaction will do the opposite. So what kind of a shift will we have? Decrease reactant, we're going to right shift. Okay, lower the temperature. Heat is still a reactant, but in this case, we are lowering the reactant. Reaction will do the opposite, and we will have what? A left shift. Okay, all right, so y'all do 9.28, and then I'll just write the answer because I think y'all know how to do it by now. So y'all do it real quick, and then I will give you the answers. Okay, so what do you get for A? A is what? A right shift. Good. B, a left. C, right. And then D, right. Y'all got it. Awesome. Okay, so why does this matter? Right? Like, okay, that's cool. In a chemical reaction, I can do that. In a reaction vessel, I can change the temperature, you know, that kind of stuff. It's really cool as a chemist. But like, how does that apply to your body? So when you exercise, right, you have to use reactants in order to make a product. The product is energy, right? If I want to be able to go from here to the education building, I'm going to have to exert energy in order to get there, right? So I need to consume some kind of food to give me an energy source like glucose. And then I need to breathe in oxygen. Those are my two reactants. And I'm going to make energy in the form of ATP. But I have some waste products too, right? As waste products, I make CO2 and I make water. This is the equation for cellular respiration, right? It looks pretty familiar to you. So why do you breathe faster when you exercise? Like if I walked from here to the education building, my breathing rate isn't really going to change. But if you see me running to the education building, by the time I get there, I'm going to be breathing heavy, right? Why? I'm expending more energy. So the more you exercise, the more you exercise, AXE, exercise, the more energy you expend. That's true. So what are you doing? You're using this up, right? You're making it, but then taking it away. So the reaction is going to shift this way, right? But what's my problem? I'm going to start using up all of my reactants. Can I replenish them? Sure. By doing what? By breathing and by eating. So that's why we eat periodically, but we consume that O2 a whole lot faster, right? So you need to breathe faster. So the more you exercise, the more energy you expend. Therefore, you need more O2 to be converted to energy to not pass out, right? What happens if you stop breathing? You will pass out, right? If you go a long time without eating, you're going to pass out. And the more you exercise between not eating and not breathing, the faster you're going to pass out, because you need that for cellular respiration. Okay. Oh, that's kind of cool. It's a real practical application of chemistry. All right. So remember how we talked about there are strong acids and there are weak acids, right? And you know your strong acids and then everything else is weak. Well, that's true. But there's a range of weakness, right? Some things are really weak and some things are just not quite strong, right? So if you look on your best friend, look on your best friend at table 9.6, this table right here, it's on your best friend. You'll notice that you have your list of names of acids. These are all weak acids. You have their formulas and you have your Ka values. But what's here that's missing on your best friend? Increasing acid strength. So things that are at the top of this table are very strong. Things that are at the bottom of this table are very weak. But let's talk about that. Who's at the bottom? Water. When you think of water, do you really think of an acid? No. Water can really either be an acid or a base. It's really on the edge. So it's really, really, really weak. How weak is it? How weak of an acid is it? If you look at that ratio of products to reactants, is that number going to be small or is that number going to be big? So if you look at our K value, and we call it for an acid Ka, do we have a lot of product or a lot of reactant if we have water? Is water going to disassociate? The more you disassociate, the stronger you are. Is water going to disassociate very much? No. So you're going to have tons and tons of reactant, right? Tons of it. And very, 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 very little product. How little? This ratio of products to reactants in water is 1 times 10 to the negative 14. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros and a 1. So are you making a lot of product? Not at all. You are barely making any product. So water is super weak. Water is the weakest. The weakest, right? If you remember that, you know the order. Because if water is the weakest, what has to be the strongest? Hydrogen sulfate ion. Now I say that, it's the strongest. It's the strongest weak acid. Is it a strong acid? No, it is the strongest weak acid. Oh Lord, right? All right, so you have to be able to look at the different acids and determine which one is going to be stronger. So all you have to do is go find them on the table and read the table. So HCN and H2CO3. So we're looking at HCN and H2CO3. So H2CO3. So these are the two, carbonic acid and hydrocyanic acid. Which one is stronger? H2CO3, carbonic acid. When you have that table and you know the direction of the table, you're good. H3PO4 or H2PO4. I can't erase all the other writing, but I can at least erase this one. Okay, so we have H2PO4, and then we have H3PO4. So we're comparing phosphoric acid and dihydrogen phosphate ion. Which one's stronger? Phosphoric acid. Ooh, I'm like writing all the way down. I don't know why it's doing that. Okay, then the last one is HCl or HSO4. Now, I know you know something. I bring clay, right? What is HCl? That's a strong. Oh my gosh, I'm all the way over here and I'm comparing that to HSO4 minus. HSO4 minus is right here, our hydrogen sulfate ion. Which one is stronger, a strong acid or a weak acid? A strong acid. So anytime you see a comparison where you have a strong versus a weak, your strong trumps. Okay. All right. So now, remember when we were talking in our iClicker questions about what happens to an acid in water, right? When an acid disassociates into water, it becomes a what? Conjugate base. When you have a base that's put in water, guess what it becomes? Conjugate acid, right? Okay, so we have to be able to look at reactions and say what's happening, what's behaving as what. And this is really similar to what we did in the very, very beginning. So look at H3PO4. What happens to H3PO4 in this reaction? Does it donate a proton or does it accept one? This one donates. So something that donates H plus is called a what? This is going to be an acid. So here we have the acid. H3PO4 is the acid. What is H2PO4? The conjugate. These always come in pairs. An acid always has a conjugate base pair. A base always has a conjugate acid pair. What's the difference between an acid and its conjugate or a base and its conjugate? One hydrogen ion. So the difference between our acid and our conjugate base is one hydrogen ion, right? So what about water? How is water behaving? It does what? It accepts. a hydrogen ion. So if it accepts a hydrogen ion, what did it start out as? A base, and it turned into a conjugate acid, and that's the water. I can't squeeze it all in. So look at B. CO3 2 minus plus water yields OH minus and HCO3. What I like to do is I like to just look at that and say, okay, which one is closest to CO3? HCO3. So what happened there? I lost, or I donated, keep the same vocabulary, donate H plus. So if I donate, I did not donate. I'm writing the wrong thing. I what? Accepted. So what am I? A base, and I make a conjugate acid. So then what is water? Water is my acid that donates the hydrogen, and we turn into a conjugate base. Isn't that cool? Okay, last one. H3PO4. H3PO4 turns into what? H2PO4. So we donated a hydrogen ion because we lost one. So the H3PO4 is the acid. So it's just like A, and we're making a conjugate base. But in this case, now we're not putting it in water. What do we put it in? NH3. Our NH3 can then pick up that hydrogen. So the NH3 is the base, which turns now into the conjugate acid. Pretty close to what we were doing in the very beginning. All you're doing now is identifying that other species on the other side of the equation and saying it's the conjugate. Not bad. Okay. All right. So we're going to end there for today. And we will pick up on the rest next time, because I want to stay and I want to talk to the people who are on Zoom and tell them all the things that they missed at the very beginning. So I'm letting y'all go because y'all heard it. All right. So how many people we got on Zoom? We got 5. All right. I don't know what happened with Zoom, you guys, but I want to show you what everybody else saw at the very beginning. So there are 2 really important things, and you can put things in the chat. I promise I'm going to pick the chat back up. Okay. So there are some things on Moodle that I want you to see. Okay. Let me pull up my chat again. Here we go. Okay. So if you look on the Moodle page, you'll see all the topics. So there are 2 topics that I want you to focus on at the bottom. It says final exam and it says extra quiz. So this extra quiz, we were supposed to cover 10 chapters in the semester, but we're only getting through 9. So to make up for those lost points, what you're going to do is you're going to do this little quiz. And this little quiz has to do with research that we're doing on basically how we learn and how we teach and that kind of thing. So trying to make us better instructors for you guys. So it's part of a research experiment. And so if you want to participate in the experiment, you have to complete this consent form, and you have to sign into your Nichols email to make it work. So if you want to participate, which I would greatly appreciate if everybody would participate, I'm not using your name or anything like that. I'm just using your data, and you can consent to participate. But whether you consent or not, everybody in the class needs to complete this quiz. Now, this quiz is not graded in terms of, did you get it right or wrong? You know, I want everybody to try. but it's either a done or not done. So either you get a 0 or a 20 out of 20. So it's a really good way to pick up a little bit of that homework score. And it is due on Friday, December 10th at 9 p.m. Shouldn't take you too long. The average is about 20 minutes, but some people take longer. So make sure you have a good 45 minutes just in case. So if you have any questions about that, let me know. But the quiz is required. The consent form is if you are willing to participate, which I would really, really appreciate. The last thing is the final exam is coming up, right? Next Tuesday is our exam 4. Then we have Thursday, which is 1 review day. Then we have Friday, which is the final exam. So because y'all are 5T, your final exam is Friday, December 10th from 10:30 to 12:30. So it happens really, really quickly. So what I did was, this has been up since the beginning of the semester. There's this set of practice questions for the exam. Now these questions will not be the questions that are on your exam. They are similar, they cover the same topics, and they're in the same format. So they're good practice. So I gave you not only the questions, but I also gave you the answers. So this is the link to the questions. This is the link to the answers. And when you read up here, you'll see these questions cover 1 through 9. Chapter 10, we didn't get to chapter 10, so don't worry about chapter 10. We're just doing 1 through 9. So what you get on that file is just 1 through 9. All right, and then the last thing is that on that Thursday after class, the Tutorial and Academic Enhancement Center is providing a free Chem 109 review session. And it's that same Thursday, but from 4 to 6 p.m. in the library. So if you want to participate in that, which they have all of my material, they have everything that we normally do in class. You go here to the flyer or the link, scan the QR code, and it will take you and you can sign up. And it is free. And it's good. So those were the things I covered with the class before we figured out what was happening with Zoom. So does anybody have any questions? And you probably have to type them in the chat because I don't know how to make the audio work over here. I'm sorry. Okay, so if you don't have any questions, you are free to go. Just remember to do this quiz before Friday, December 10th, 9 p.m. And y'all have a great rest of your day.